Okay, so let me now go back a little bit to the substitution rule and to explain something about it before going to the next topic. I would like you to think about calculus and the tools we learn within calculus as really tools, because, well, calculus is going to be a tool for you in the future. And there is something you would probably want to know about a tool, about any tool you're going to use. Right? There are three questions I would like to emphasize about any tool. Right? If you learn a tool, if you have a tool, what is it that you want to know about it? How it works, how to use it, how to use it, when to use it, and why to use it. Right? So you should recognize when is it that you may want to use it. Right? You should understand why you may want to use it, what kind of benefits application of this tool will give you, and of course you have to know how to use the tool. And I would like to apply these questions again and again for the tools we learn. And of course, the more complicated tool is, the more complicated the answers are going to be. But I would like to begin with simple things, simple tools like substitution rule. Right? Substitution rule is a tool, can be considered as a tool. Right, so it comes from differentiation. In differentiation, we have chain rule. And then in integration, we have this substitution rule. And those are about the same thing, about the same phenomenon, about composition of functions. Right? If you see a composition, how would you differentiate or how would you integrate? So I described previously how to use, right? And they will usually begin describing the tool by how to use it and give you some examples. And then talk more about when and why. Now, why would you use substitution rule?
Because sometimes integration is impossible without it.
Because sometimes you look at the integrand and you don't know how to take antiderivative, how to find antiderivative, and you would like to at least simplify it. Right? So you want to simplify. So you want to simplify the integrand. And to simplify for the single purpose of computation. And that purpose is going to be the main purpose for this course until we get to the point of understanding better and getting to conceptual aspects of integration. So that reason why is going to be for computation. But there is another reason to use the substitution rule, and that is for better understanding of the integral. So if you want to understand better, and you try to understand the integral better, you may want to consider the intermediate variable, the variable that you used during the substitution, and you might want to consider that as a new good variable to look at. So you might want to introduce a new important or potentially important variable. And now the when aspect, right? I would like to think about it as your ability not to apply the tool, not to go step by step and crunch that substitution procedure, but to estimate, to evaluate quickly whether that application is going to be useful or not. And I think that is one of the crucial abilities about any tool. You look at the situation and you estimate quickly whether substitution is useful or not. And then, based on that evaluation, you go ahead and proceed with the whole long, maybe tedious process. But how do you estimate? How do you decide when you should or maybe should not?
When the integrand is a composition of functions, we can always try.
Exactly. You look at the integrand, and it should look like a composition of functions. Well, of two, right, functions. And then that's exactly how you decide if you want to try or not. If it doesn't look like a composition, you shouldn't try. If it does, then you should probably try and see what happens. And, well, let's try an example. X cubed times e to the x squared dx. Just try to find the indefinite integral. So you may want to look at u equals x squared. And of course, when you look at this integrand, it doesn't look like a composition of this function and something else. If it was x squared e to the x squared, it would be a composition. It would be u times e to the power u. But now it is not. But there is this major part, right, that you want to simplify. X cubed is already simple enough. You want to simplify that, and that has that x squared, so that's why you may want to look at this as almost a composition. So looks like means that at least a part of it, the complicated part, is a composition, but the rest may not be. And then you go ahead with this computation of du, which is 2x dx, and then you try to write down the integrand separating x dx part. So you can take one x out of there and see that x dx is exactly a half of du, and the remaining part is a function of u, so it is u times e to the power u. And then you finally decide whether you want to apply this substitution or not. At first we did some estimate, but now we decide by looking at this function and deciding, well, is this function simpler than what we had before? And apparently, yes, it is simpler. Because sometimes it is not going to be simpler and this substitution doesn't work, and you may try a different substitution. So let me keep this as a framework of how to look at the tools. And the next tool we are going to use is also coming from differentiation.